How do we feel about quantum mechanics so far? Thumbs up? Not too bad, right? Okay, the third postulate is the fun one. So the third postulate is about measurement. So chapter 2.3, quantum measurement. This is where things get interesting. So the measurement postulate says the following. Measurements, which, in a classical system, I would measure the temperature of this room. I would, bring in a thermometer and see what the reading is. Measurements are going to be a little bit different in quantum mechanics. So measurements are described by a collection of what we call measurement operators. Collection of measurement operators, which we'll always use the notation M sub M. So capital M referring to the operator, little m referring to just an index, which operator it is. And I could go from m being 1 to some number of operators, n sub m, that we have. So the little m indexes the measurement outcomes, and the capital M is the measurement operator itself. So any measurement operators like this will define a valid quantum measurement as long as the following condition holds. So we need the sum over all little m of m dagger m equal to the identity. This is known as the completeness relation. So it's a complete set of measurement operators. Now, if we're in a state psi, in the state psi, measurements are always with respect to a particular state. So in the state psi, the probability of obtaining measurement outcome m, so the probability of obtaining measurement outcome little m, is equal to this inner product, this overlap, bra psi m dagger m psi. So already it's a very interesting thing. Quantum mechanics tells us that outcomes of experiments, measurement outcomes, aren't deterministic. They occur with some probability. So the best we're able to say is the probability of a particular outcome happening. We're never able to say, given a particular experiment, which outcome will happen. We can use statistics, of course. Given a large enough number of experiments, large enough number of measurements, they'll agree with the measurement outcomes as we're writing the rule here. But given a particular experiment, the best we can tell you is the probability of all the outcomes happening. In addition to the probability of the outcome, there's another rule that the state after the measurement, state after measurement, so let's say the state after measuring outcome m, state after obtaining the measurement outcome m. So let's suppose we do an experiment, we make a measurement, and some outcome little m happens. What state do we get? Psi gets mapped to, so psi transforms to the state, the operator m sub m acting on psi, and then I need to normalize it by the square root of the probability p sub m. Quite a strange postulate, but this is what we have in quantum mechanics. You have to see an example of this to see how this works. Just a quick remark before that. Why would I require this completeness relation? Well, it's going to be that given this rule for the probability, which involves these products dagger I want the sum of all probabilities to be 1, right? Something has to happen when we do an experiment. quantum measurements are weird, but they're not that weird. So something has to happen. We have to get some measurement outcome. That means if I sum over all the probabilities, I should get 1. If this happens for every state psi, which it shouldn't matter what the state psi is, the sum should always be 1, then you can see from this equation that we must have this completeness relation just in terms of the operators, not in terms of the state psi. Okay? So this comes from the requirement that the sum of the probabilities must be 1. See an example? So the example is going to be, let's stick with the single qubit case. So measure a qubit in what we call the computational basis. So the computational basis. And that we've been seeing as 0, 1. So what does it mean to measure in a particular basis? We'll write this down formally. In the next few sessions, we'll cover measurement in a lot more detail. But this means that there's 2 measurement outcomes. There's M0, and it's going to be this outer product, which is going to be the projector onto the 0 state, on the 0 qubit. And M1 is going to be equal to the projector onto the 1 state, the ket 1. So let's check that this is a valid measurement operator. What do I need? I just need this completeness relation to hold. So if I do that, I sum M0 plus M1, then this is equal to the outer product 0, 0 with 1, 1. As matrices, you should know or be able to compute that they evaluate to these 2 matrices. And you see when I sum these together, I do indeed get identity. So this is a valid set of measurement operators. This is a valid measurement that we can make. Let's be general, and let's say that we're in the state psi, which is just alpha 0 plus beta 1. Remember, measurement is always with respect to a particular state. So using this state and the measurement operators, try to work out, using the measurement postulate, what the probability of measuring 0 is and what the probability of measuring 1 is. Take a few minutes to yourself to try to work this out. All right, so let's see how this one goes. I'll work out one in detail, and I'll leave you to work out the other one. So let's try working out the probability of 0. Where do I start? I'm going to use our rule. We have a rule for this. So this is going to be equal to psi, m0 dagger, m0 psi. Now, there's a few ways you could go about this. With experience, I'm going to know that m0 is Hermitian. So the dagger I don't have to worry about. And furthermore, it's easy to evaluate the product of m0 with m0. What's that going to be? It's just going to be m0 again. Do you see that? It's because, so this is going to be equal to, I can simplify, psi times m0 times psi. That's just because the inner product of 0 with itself is 1. So let me write that out. The inner product. So m0 is Hermitian. And furthermore, 0, 0 times 0, 0. I can single this out in the middle. That's equal to 1. This is a normalized quantum state. Just from the vector, you should be able to work out this is 1. So this is equal to 0, which is just m0 again. All right, so I can simplify here. And now let's write out what the thing is. So I'm going to have 2 inner products, psi with 0, and then 0 with psi. Who could tell me what either one of these is? For example, the first one. So psi inner product with 0. Or let's make it even easier. Let's consider bra psi inner product with ket psi. So ket psi is written here. If I did an inner product with bra 0, what would I get? Just alpha. Does everyone see that? Why is that going to work? It's because 0 and 1 are orthogonal. So formally, we could write this as 0 psi is going to be equal to, I use linearity, so it's going to be equal to alpha 0 inner product with itself plus beta 0 inner product with 1. This one goes to 0. This one is equal to 1, so this is just alpha. Okay? So this I can replace with alpha. And then you could do the same thing here, taking complex conjugates, or you could realize that this is the complex conjugate of this. Do you remember the rule for Hermitian conjugates? I change the order, and then I take the conjugate of each. So ket psi becomes bra psi on the left, bra 0 becomes ket 0 on the right. So this one is equal to alpha star, complex conjugate, times this one is equal to alpha. And this whole thing is mod alpha squared. Okay. So in the state psi being equal to alpha 0 plus beta 1, probability of measuring 0 is mod alpha squared. And you should be able to work out in a similar way that the probability of measuring 1 is mod beta squared. You see from the first postulate now why we have this condition. So we require that alpha squared plus beta squared is equal to 1. This is, again, a statement about the probabilities. So as long as the measurement outcomes satisfy the completeness relation and the state satisfies the unit vector condition, then our measurement outcomes make sense. You also see why we have the unitary evolution postulate, postulate 2. Remember, unitary, unit in unitary is referring to unit vectors. So unitary matrices map unit vectors to unit vectors. That means the probability is never going to change. We're always going to have a sum of probabilities being equal to 1. The probability of particular states, of course, is going to change. That's what unitaries are going to do for us. But the sum of all probabilities is going to remain at 1. OK, the last comment to make here is that the state after I measured 0 should be the following. So let me make a little more space. And let's suppose now that I measured the state 0. What would the resulting state of the system be? Well, using the rule again, psi being equal to alpha plus beta is going to go to m0 applied to psi over the square roots of p of 0. And if I do this, let's write it out. So I'll have the operator m0 is 0, 0. Psi is alpha 0 plus beta 1. And then we just worked out the probability is mod alpha squared. So the square root of that would be mod alpha. Now we just have to apply this projector, this outer product, to the state here. Again, using linearity and orthogonality, this term is going to stay. This term is going to get killed off. So this will be equal to alpha 0 over mod alpha. Okay? So if I measure outcome 0, I end up in a state that's essentially 0. The only potential change is what we'll come to know as the phase can change. So it's going to be proportional to the state 0, but we're going to be allowed to have some other complex number out here, which we'll call a global phase. Make sure you can work out the same example of this for measurement on the one state. And make sure you could go through this example if I gave you another measurement basis. So we did it for 1 here, but you consider a general state. Make sure you could follow the same reasoning for a different measurement basis, for example, measuring in the plus-minus basis.